So we are dealing with the problem solving session on gravitation, and let us begin with the first problem of this series. The first problem for this one is problem number 1.191, and the problem is asking a particle moves along a closed trajectory in a central field of force where the particle's potential energy U equals kr square, where k is a positive constant, r is the distance of the particle from the center O of the field. Find the mass of the particle if its minimum distance from the point O equals r1 and its velocity at the point farthest from O equals v2. So before we start approaching this problem, let us begin by drawing a necessary diagram of the situation. So what we have done is we have marked the trajectory of the particle. So this is the point O about which the particle is moving in the closed trajectory in the central force field, and this is the first position of the particle, which is the distance of closest approach, and this one is the farthest distance. The velocities and distance from the point O, which is the point of focus of the ellipse, is marked. Now apart from this, the problem is stating that the potential energy U is varying as kr square. So this is the information that is given in the problem. So therefore, from the definition of force, we can say F equals minus du by dr, and therefore we can say that F equals minus derivative of kr square with respect to dr, and we obtain F equals minus 2kr. If I write just the magnitude of force, so the magnitude of force can be written as 2kr. This is a part of the problem which we consider. Now over here, find the mass of the particle. The problem is asking us find the mass of the particle if its minimum distance equals r1 and its velocity at the farthest point equals v2. So since the question has already stated that the particle is moving in a closed trajectory in central field of force. So if the field of force is central, then for all these central forces, we can apply angular momentum conservation. So since the forces are central, we can apply angular momentum conservation. So L at point 1 must be equal to L at point 2. The angular momentum is conserved, and therefore we say that m v1 r1 equals m v2 r2. This we refer as equation 1. The next one that we do is we say that the energy is conserved. So conservation of energy is the next equation that we are going to write between the point 1 and 2. So total energy at 1 must be equal to total energy at 2. So if we write total energy at 1, so total energy at 1 equals half m v1 square. Now since potential is given to us in terms of k and r square, that is kr square, so at first position we will have this one as k r1 square, and then we write kinetic energy at 2, which is equal to half m v2 square plus k r2 square. So with these two equations and the expression of force that we have, which is equation A, we have three equations. Now the next thing that we do is that at the point 1 there is a radial force which can be written as 2kr1. So if I write over here from this part that the force at point 1, then the magnitude of force at point 1 can be written as 2kr1, and the magnitude of force at point 2 can be written as 2kr2, and at both these points it is balanced by m v1 square by r1, and it is balanced by m v2 square by r2. So using these two expressions, we can frame another expression with respect to r1, that is 2k r1 is also equal to m v1 square by r1, and this we are referring as the third equation. Now the problem wants us to evaluate the mass of the particle. So if we solve these three expressions, we will end up with the mass. Hence, we obtain the mass m equals 2k r1 square by v2 square. So we need to give our final answer in terms of r1 and v2, and we have three unknowns r2, v1 and m. We can solve for each of the variable, and then we solve for the mass which is the asked in the problem. So m equals 2k r1 square by v2 square, and this is the final solution for this particular problem which we have discussed, problem number 1.191.